And now, a reaction. Now, this is actually a reaction for those of you in lab that you did in the pottery and pigments experiment. Sort of, kind of. You had a lead salt, in this case, we're going to use lead nitrate, which is not what you used, and potassium iodide. And what happens? So I will tell you that both of these are ionic compounds, and they are both clear and colorless, and they dissolve quite nicely in water. So that's clear. So a solution of both of these are clear and colorless, and when you react them or mix them together, you get this very bright yellow solid. So let's do this in equation speak here with pictures. So it looks kind of like this. So clear, colorless solutions, mix them together. The solution remains colorless, but a very bright yellow solid has been formed. And what that is, that yellow solid is lead iodide. And this is an example of a precipitation reaction, which is the first class of aqueous reactions that we are going to study in this chapter. And by the time we're done, part of the next exam is going to be a series of questions like this, where I just give you some products, some reactants, and you're going to tell me what the products are. And so these precipitation reactions are the first one. So first order of business is to define a precipitation reaction. So here we go. These are reactions that result in the formation of an insoluble product, so something that doesn't dissolve in water, from things that did, from soluble reactants. So both of those criteria need to be met. An insoluble product and soluble reactants. So on the molecular level, what's going on here? So we talked about the reason why sodium chloride dissolved nicely in water is because the interactions between the ions in the water were stronger than the interactions between the ions and themselves. That's not always the case. In some cases, the ion-ion interactions are sufficiently strong that the interactions with the water are not, they're stronger than the interactions with the ions in the water. So the solid is not dissociated in that case. It just sort of sticks together, and in many cases just sinks to the bottom of our beaker. All right, another definition here. We talk about this term solubility, and all this means is it describes the amount of substance that can be dissolved in a given amount of a particular solvent, and it's something like 0.5 moles per liter or something like that. And if the maximum concentration that you can achieve for a particular solvent for a particular solute in a particular solvent is less than 1/100th of a mole per liter, we're going to call that insoluble. Now, to correctly predict if a ionic compound is soluble or not, well, you generally can't tell just from the formula. Basically, you have to do the experiment. The bad news is there are, only a few 100,000 known ionic compounds. The good news is that people have already pretty much done the experiments and thankfully written down the results. So you actually don't have to do this, but you'll be held responsible for knowing the result. Not all of them. And so what I'm going to show you now is the next two slides go over a bunch of rules that will tell you if a certain ionic compound is soluble in water or whether it is expected to be insoluble in water. And it's actually not that tough a list. It's only about 10 pieces of information that you need to know. And I'm going to give them to you in decreasing order of precedence. Namely, that the rules I told you, the first rules that you're going to see are the most important. they are the ones that are not broken, and anything else, any other rules, further rules become subservient to the first ones. Namely that if there is a inconsistency, go with the earlier rule. All right, so on this slide, I'm going to talk to you about cases where you will know for sure that the compound is soluble. All right, so here we go. If the anion is nitrate, no matter what the positive ion is, if it's nitrate, it's soluble. If the anion is acetate, so this is actually that leftover chunk or that leftover bit of acetic acid. Its formula is C2H3O2. Also, no matter what the positive ion or the cation is, that compound will be soluble and will dissociate. Also, if the cation happens to be ammonium, NH4+, so that's one of the lists you're supposed to know, or any of the group 1A cations. So this is that first group all the way on the left. So that is like lithium, sodium, potassium, and those guys. If that is the cation, no matter what the anion is, that's going to be a soluble compound. And also, a couple more, also from your polyatomic ion list, perchlorate, and chlorate. If those are the cations, if those are the anions, no matter what the cation is, they will also be soluble. And now it gets a little more complicated. If the cations are either chloride, bromide, or iodide, that compound will be soluble unless the cation happens to be silver, mercury, Hg2, 2+, so this is mercury 2. This is actually a polyatomic ion that consists of two mercury atoms, more or less covalently bound to each other, that happens to have a +2 charge, or lead 2. And if the cation is one of these, then the chloride, bromide, or iodide will be insoluble. Note that the other member of that group, fluoride, is not on this list. Fluorides are complicated. And lastly for this slide, sulfate salts are generally soluble unless the cation is calcium, strontium, and barium, or our mercury +2 and our lead +2. If you want an easy way to remember these three, these are all in group 2A, so the second group over from the left. All right, so these are cases where you will look at a formula and know if the compound is soluble or not. Now on this slide, we're going to look at it the other way around. So this is a list of cases that will tell you for sure that an ionic compound is not soluble in water. And the first one is sulfides. So these are generally not soluble unless the cation happens to be either calcium, strontium, or barium. So again, remember, these are the heavier members of group 2, or ammonium, or the alkali metal cations. Now, if you think about it, this first line here, ammonium, alkali metal cations, is merely a restatement of the solubility rule from the previous slide. So this is actually not a new piece of information. This takes precedence over sulfides, and this is just a new adjustment to that. So carbonates are also generally not soluble. In fact, actually, things that are not soluble in water are often called rocks. And in many cases, actual rocks consist of carbonate and other things in there. The notable exceptions are if the ion is, if the cation is ammonium or any one of the alkali metal, the group 1A ones, sodium, lithium, potassium. So again, this is just a restatement of the first rule we had. Phosphates, pretty much the same thing. They are generally insoluble and also often rocks, unless the cation happens to be ammonium or any of the group 1A or the alkali metal cations. Phosphate is actually a big part also of bones and teeth. And if you think about it, it is, given that we are mostly water, it's pretty good that the support structure is not water soluble. Otherwise, we would have problems. Hydroxides, this is going to be the last one. Hydroxides are generally not soluble unless the cation happens to be one of the group 1A metals or the heavier group 2 metals. So this is a very similar exception to the sulfides as well. So again, if you remember that this slide, if you remember that ammonium and the alkali metal cations are always soluble, that takes care of actually the sulfides, the carbonates, and the phosphates, and that just leaves you to remember that calcium hydroxide, strontium hydroxide, and barium hydroxide kind of soluble. You'll be held to those pieces of information. So if I give you any of the compounds, any ionic compounds that are described by these rules, you're going to need to be able to figure out and tell me if that compound is soluble or not. So let's go through an example of one of these to kind of see what you're going to be expected to be able to do.